All right, in this little video lesson, we're going to go over example 2. This is simply a single stage material balance for liquid-liquid extraction. And the problem statement reads that pure isopropyl ether, which in my graph is designated as S, is added to a stream that contains 50% water with 50% acetic acid. In this case, A is my acetic acid and D is the water. And the resulting mixture is going to contain 40% isopropyl ether. It is then allowed to come to equilibrium where the two liquids are formed. These are separated as an aqueous product and an organic product. If the isopropyl ether solvent rate is 100 kilograms per hour, what is the flow rate of the water acetic acid feed? And then we'll follow that up by looking at what is the composition of the aqueous product and what is the flow rate of the aqueous product. So here we have graphed the data for the system, designated at A, D, and S, matching the nomenclature in OneCat's textbook. The feed is 50% A with 50% D. The solvent is pure and it's flowing at 100 kilograms per hour, and my resulting mixture will be 40% S. So let's try graphing these on this diagram. So if I'm looking for something that's 50% A with 50% D, it's going to be on this edge that's on the far left side of the screen. And 50%, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 50% is right there. So it's 0% S. It's halfway across on the acetic acid water line. My solvent is pure S, so it's going to be this opposite corner. And if I connect these with a straight line, the resulting mixture has to be on that line. We also know that it's going to have a composition that is 40% solvent, so right there. Okay, so this is my feed, this is my solvent, and this is the resulting mixture. I can figure out the quantities in each stream by doing a material balance. So there are many different balances we could do. What it turns out is going to be easiest in this particular case is to do a balance on the solvent. And in the solvent, there's 0 solvent in the feed, and there's 100% solvent in stream S, and it's going to create a mixture that's 40% in the mixture. We know that S is equal to 100, so 100 equals 0.4 m. M, therefore, is 250 kilograms per hour. And we also then can do a total material balance, which says that F plus S equals M, and so therefore F is equal to 150 kilograms per hour. Now we know that this is going to split into two phases because it falls in the graph in the region that is two-phase, where we've got all these tie lines. I'm going to find what my composition is of the two different mixtures by approximating or visually interpolating what the tie line should be that will pass through that point. And I've drawn it in right here. So it's just barely above an existing tie line. I can mark the two endpoints. The material that's coming out that is most like the feed is going to be the raffinate, and it is on the left side of the graph. And the material coming out that is most like the solvent is the extract, and it's coming out and it'll be on the right side of the graph. So we have these 2 points shown here. If you wanted to know the composition of the aqueous phase, So the aqueous product is going to be the one that has the most water in it. Pure water's here, so something over towards this lower corner, and that's the raffinate. So this is going to be the aqueous phase. And the extract will be what they'll call the organic phase, because it's heavy in the solvent. It's close to the corner that's 100% S. So I can find the compositions of these by reading off the point here. So this point here, the composition looks like it's about 4% solvent. It looks like it's 10, 15, 20, 25, 30, 35, about 38%. I may be a little low on that. 38% acetic acid, and the balance will be water, so roughly 58% water. So that's the composition of this stream. Now, to find out the flow rate of the aqueous product, I could also find the composition of the organic phase and complete material balances, or I can do this the lever principle. So if I solve this using the lever principle, what I do is I need to measure this. So you need to get a ruler out, but you probably just drew straight lines using that ruler. So this is, you've got the materials handy. And what I'm going to do is I'm going to measure the screen. So across the full length of the line from R to E, looks like that's 7.6 centimeters. Now obviously this is going to be different on whatever device you're using. I'm using an iPad at the moment. If I want to know what the flow rate is of R, I'm going to find the length of the lever arm on the opposite side, so M to E. And that length is 3.3 centimeters. Okay, now what this lever principle tells me is it tells me that the amount that's flowing in the stream R compared to the mixture is going to be the length of the arm ME compared to the length of the total tie line. Okay, so this is 3.3 over 7.6. This is R, my unknown, over 250. And so therefore R is equal to 250 times 3.3 divided by 7.6, 109 kilograms per hour. Now this is going to be pretty rough because we're doing it from measurements here. I'm going to argue that even if you think that it's more accurate to do material balances, you're still reading compositions, so it's not going to truly be much more accurate. I would say that the answer is going to be 2 sig figs, 110 kilogram per hour is what I'm having flow in the raffinate. So this completes this little example. In the next little video, we're going to take a look at cross flow and then counterflow extraction.